Okay, so thank you, Jakub. So today I wanted to give a talk about Grizzly, some Grizzly overview. Really, I didn't want to go into much details, but just really overview Grizzly features, some description, brief description, and yeah, that's how I planned this to be done. So on our agenda today we have introduction, then we'll discuss the Grizzly core module, Grizzly HTTP server module, talk about WebSockets and port unification. So I took these modules as most important in Grizzly and most useful. And yeah, if you have some additional questions, just yeah, don't hesitate. Just stop me at any time and just ask your question. No problem. So let's start. So what is Grizzly? Grizzly is an open source NIO framework, which is supposed to hide Java NIO complexity and propose more user-friendly API. And as I said, like Grizzly open source framework, it's licensed. It's licensed under two licenses. It's CDDL and LGPL. So we can choose one of those. It's yeah. We have very open community. So all the feedback, questions, we are trying to respond as soon as possible. So if you have any questions, like even some specific to your application, just you can ask and we will try to help you. Historically, like Grizzly project, it's like we've started it like, I don't know, 7 years ago. The former Grizzly lead, Jean-Francois Arcand, maybe you guys know him. He's currently leading Project Atmosphere. And he started Grizzly like 7 or 8 years ago. I don't remember exactly. So, and at that point of time, it was a fork of Tomcat. So he took Tomcat and implemented NIO connector for Tomcat. And after that, he took this NIO connector and created open source project named Grizzly. So originally it was taken from Tomcat. And then from that project, we took that project as base for Glassfish application server. So it's like we took it from Tomcat, based our core framework, and delivered it to Glassfish as a network framework. So we have currently two main branches on Grizzly. It's 1.9.x, which we are still supporting. It's older API, but we still, like as I said, we support it. And Grizzly 2.0, it's a newer branch where we are currently working on, and we are like all the new features we are delivering under 2.0 version. So yeah, just to repeat myself, Grizzly framework has been designed to help developers to take advantage of Java NIO, but at the same time we hide NIO complexity and propose more useful and user-friendly API, which helps users to create scalable and robust client and server applications. So here we'll talk about just main modules, Grizzly modules, which as I mentioned are most useful in Grizzly. First of all, it's Grizzly core module. We call it NIO framework of core module, where we support support by default TCP and UDP transports. As I said, we are hiding socket NIO complexity and proposing our connection and transport API. We have efficient buffer management. So we are not just some detail. We do not allocate buffers all the time. Grizzly needs it, but we keep a thread local pool for buffers, and we try to reuse some thread local buffers. So as much as possible, if it's not possible, we are going to another pool, which is not thread local. So access to that pool is a bit more expensive. And if that pool also doesn't have any buffer, which is good for us, we are allocating new buffer from JDK. It's our default implementation. And we also, in the core module, we have support for port unification, which gives the possibility to serve different protocols on the same TCP port. We can think about HTTP, HTTPS, IIOP protocols to be served on the same port, which makes it easier for administrators to keep just one port open for internet, for example, instead of having a couple of ports open to internet. So it makes life easier for administrators, as I said. Other than that, we have HTTP framework, which is also pretty useful. And it looks pretty similar to Servlet API, to Servlet framework. But additionally, or unlike Servlet framework, we provide NIO features in our framework. So you can think about Grizzly HTTP framework as Servlet. Its API is similar, but we also propose NIO compatibility there. So it's possible to leverage NIO in our HTTP framework. So on top of HTTP framework, we also implement Comet and WebSockets. So this is how Grizzly looks like, the picture. So here we have core framework, the green one. So on top of core framework, we build port unification and HTTP codec modules. And on top of HTTP codec module, we build HTTP server, which then is derived by WebSockets and Comet. Here we do not have, for example, HTTP client module, which we also have. So it will be like another rectangle here, which is derived from HTTP codec. So we share the same HTTP codec between server and client implementation. So let's talk about Grizzly Core. Two most important abstraction on Grizzly Core is transport and connection. So when we talk about transport, it's you can think about TCP, UDP. So Grizzly supports TCP and UDP transport, and we have NIO implementation of the transport. So it's TCP NIO transport, UDP NIO transport. So each transport may have some connections associated with the transport. So when talking about connection, we can think about socket. So it's the same. So Grizzly connection is pretty much similar to what socket is. And relationship between transport and connection is one-to-many, as we understand. So we have TCP transport, which may have number of sockets associated. So in Grizzly, it's the same. We have transport and number of connections associated with the transport. Okay, next slide. So like Zbigniew, the presentation which was before mine, Zbigniew described netty abstractions, and he mentioned protocol chain or some some handlers, but so he handlers in the chain, right? So in Grizzly we have absolutely the same, or say similar approach. So we have filters, which is handler, and filter chain, which is, I don't remember what's the name of abstraction. No, it's not a channel. Channel is Grizzly connection. So, but anyway, it's like pretty similar. So filter chain, which consists of filters. So filter chain, similar as in netty, each filter in chain represents some processing unit. It's some logic which transforms one message representation to another. So say we have byte array and we want to transform it to HTTP message. So say HTTP codec message is responsible to make this transformation, and backwards as well. So if we have HTTP message, we want to transform it back to byte array to send it to network. So it's what HTTP codec is doing. So here we have an example how HTTP server filter chain may look like. So first of all, we have transport filter, responsible for reading and writing data from network. Then we Then we have HTTP codec filter, which is responsible for transforming byte array to HTTP packet and vice versa. And then we have HTTP server filter, which knows how to process HTTP requests coming from HTTP codec and make and send proper responses to these requests. So this is how HTTP filter chain may look like. Then, so if we think about HTTPS filter chain, so it's like secured HTTP, what we have to do is just insert one more filter in a chain, which is SSL filter. So, and here we have HTTPS filter chain. Okay, it's just example how Grizzly echo server looks like. So first of all, we are constructing a filter chain which contains of two filters, transport filter. As I mentioned before, transport filter is responsible for reading and writing bytes from network. And echo filter itself, which just receives byte array and echoes it back to the channel. So here we have constructed filter chain builder and assigning it to TCP NIO transport here. So we take transport, say set processor or set filter chain, maybe it's might be a better name, and assigning filter chain there. So now we are binding our transport to specific host and port, TCP host and port, and we start in our server. So, and here how the actual echo filter looks like. So echo filter again, filter has a couple of, there is base filter, which has a couple of methods, notification methods, which are called by Grizzly to notify that some event occurred on a connection. So if connection has some data to be read, to processed, we call handle read. Grizzly calls handle read. So echo filters handle read method is going to be called. We are receiving address, peer address, where the message came from. We are getting the actual message here and just writing it back using context, using the current context which we received here. So and yeah, we instruct filter chain that here we want to stop these concrete event processes. That we say, okay, we are done. Don't try to give control to another filter in chain. So we say that we are the last filter in the chain which processed this event. Do you have any questions regarding core? Yeah. So next component, it's HTTP server. As I mentioned, HTTP server is also implemented on top of Grizzly filter chain, which I showed here. So this one, but instead of proposing user filter chain like API, like this, we are proposing user servlet-like API, which is based on HTTP handler, which is similar to servlet. So additionally to servlet, as I mentioned, we provide asynchronous and non-blocking features. So at any point, user can, there is no reason for user to block on a connection if he wants to read or write some data. So all the time we don't need to block any threads and just check if there is data to be processed, we process data. If there is no data to be processed, we just release the thread and give it possibility to process another request. So we never block on a thread and trying to reuse threads and resources as much as possible. So in order to achieve that, we are proposing NIO input stream and NIO output stream API. So it's pretty similar to input stream and output stream, but we have additional methods which allow you to figure out if you have any data to be processed on this specific stream or not. So, and in that case, you will never block on the channel, on a stream, sorry, on input stream or output stream. So the same API we propose for characters. So we have NIO reader and NIO writer API. So here, how our handler looks like. So it's simple handler which extends with the HTTP handler. It does nothing. It just you see here is the method which is getting called by Grizzly once HTTP request comes. So it's pretty similar to servlet. And here how we actually run Grizzly HTTP server. So we create HTTP server here. We have some built-in builders for that. To create a simple server. So we just pass in on which host we want to listen port. We are setting handler to the server. So we are setting simple handler, this one, to this server and start the server. So and now all the requests which are coming to this server will be passed to simple handler and processed, similar as servlets. Okay, so now we are coming to non-blocking reading. So as I mentioned, we provide this possibility for our HTTP handler API. And what's the main problem with reading in servlets is when you have stream, when you're receiving input stream from a servlet, like you are calling request dot get input stream. You are not sure if there is data to be read, to be read, or there is no data. Because if you try to read data and there is no data, you will block and wait until at least 1 byte come to this stream. So that's the most dangerous part of servlets. So because if you have a couple of servlets which process some slow clients, you can actually, and you have limited number of threads which you use to process all the requests. It means that a couple of slow clients can block entire server because they will slowly send data to these servlets and they will just block the threads. And another, for example, faster clients will not be able to get access to be processed because all the threads are occupied by slow clients. And yeah, here we are solving this in Grizzly by providing this additional read handler API. So and now you are able to, you have NIO input stream. It's not regular input stream. We have NIO input stream in Grizzly, and you are able to register read handler there on this input stream, and this read handler will be notified once you have some data to be read, or you have, or it will notify you that you don't have the request is finished, so you do not need to expect any input data anymore, or if there is some error happened, so it will be notified about error. Okay, so here it is simple example how input stream can be used and how handler can be registered. So again, we are inside service method of our HTTP handler. We are getting input stream, which is actually NIO input stream, and we say, okay, notify when you will have available, at least if you don't specify any parameter here, it means it means your read handler will be notified when at least 1 byte is available. So you are registering this read handler, and you do not care about, and you never block this thread. So, and this read handler will be notified once you have some data to be processed, and once you have data to be processed, you can process this data here. Once all data is processed, so you do not expect any additional input data, you can just resume or finish request processing. Yeah, so this is how, for example, echo. I have it here. Yeah, so yeah, here I missed it. So here, when some data is available, so on data available method is called. We are calling here echo available data just to send the client the same data he sent to us. So client sends some data to server, and server replies with the same data back. So it just takes input stream response, passes some object to notify available, to echo available data, which is here. So what we are doing, we are in input stream, in NIO input stream, we are asking how many bytes you have available to be read without blocking. So here we have number of bytes we can read without blocking. We are allocating array of this to read this data, reading data, and using output stream to echo this data back. So it's just simple implementation. It's far from being optimal. So, and here how optimal implementation will look like. So we are not allocated any additional data. We are just taking buffer provided by input stream. It could be even direct byte buffer here, and we use that possibly direct byte buffer to write this data back to client. So this is how it might be implemented. And as I said, like, these will never block. Okay, so now we are coming to non-blocking writing. So unlike reading, non-blocking writing has different issue. So when you use output stream in serverless, for example, and you want to write a lot of data there, and client is really slow client, it's not able to get this data as fast as you are sending this data. So what happens, internal socket buffer is getting overloaded, and default socket implementation will just block, waiting for this socket to be able to accept more data from you. So again, if client is pretty slow and you are just trying to, for example, to send some file to this client, it will block the thread and waiting until client slowly reading some data. So what we are doing in Grizzly, we are using NIO, so we are able to not block. But another issue which occurs is that when you are not blocking, okay, so you are able to send lots of data to client, but client at this point, client is not able to receive this data anyway. So client is slowly reading some data byte to byte, and you are sending hundreds of kilobytes to this client. So this data is getting buffered somewhere, right? And if you are writing lots of data, you may end up with out of memory error, because this data has to be buffered somewhere. So what Grizzly proposes, we have proposing write handler API, which you can register on output stream, and this handler will be invoked, will be called once this specific connection is able to send more data is able to send to accept more data from you. So in that case, you will not try just blindly send megabytes of data to the client, but you can say, okay, here I'm sending you, I have like some chunk of data, say 8K chunk. Can I send you 8K chunk? Grizzly will say, okay, you cannot at the moment. You say, okay, I'm registering this write handler, and let me know when I can write this 8K buffer. So at this point, you will not need to buffer huge amounts of data somewhere in the memory, and this way you will not end up with out of memory error. So it's how write handler may look like. So it's pretty similar to input stream. So you're getting NIO output stream and saying, okay, notify me when I can write at least 1 byte, I can send at least 1 byte to client. So, and this method, notified write possible, will be invoked, and you are able to send some data. And you can say, okay, notify me like here, you send some data, and you can invoke this method again, like saying, okay, notify me when I can send more data next time. So Grizzly will invoke that again, and you can send another chunk. Yeah, so, and these two API, like these two features, NIO reading and NIO writing, could be some building blocks for a couple of use cases you may want to implement on your server. One of them is upload, download of content, download of huge files, for example. So you will never, when you upload something, it means like you are able to read data when it comes and never block the thread. So you can just read data in chunks, save data somewhere or process the data, but never block. And the same with writing. You can write huge files without blocking and without and not like ending up with out-of-memory error. And also it can be used in all kind of HTTP proxy and tunnel implementations. So it's like pretty similar approach. So we do not care if one side of communication is able to process faster than another side. We can tune them so they can. We never, first of all, we never block when reading, and we never go into out of memory when we're writing. So it's kind of issues which might be like this one kind of features which might be useful on when implementing tunnel and proxy. Any questions so far? Oni se nedebufferujou ty data, myslíte to write, že jo? Prostě tady to řešení právě, že když používáte to řešení, tak nemusíte bufferovat ty data. Že prostě když máte nějaký soubor otevřený, jo, tak v tom případě prostě přečtete si třeba 8 KB z toho souboru, zkusíte ho poslat, když můžete, tak pošlete ho, když nemůžete, tak prostě zaregistrujete write handler a pošlete ten jako 8 KB buffer příště, až to bude možný. Takže prostě nikde to nebufferujete ty data. Že ten file je otevřený sice, jo, ale ty data nedržíte v paměti přímo, jo. Ale v tom fileu ty data jsou a vy máte jenom ten 8 KB buffer. Takže prostě, a když nebudete používat tohle z toho, tak teoreticky byste mohli jako Grizzly nebude, když se budete pokoušet poslat data do output streamu jako 8 KB, pak ještě 8, pak ještě 8, pak ještě 8, bez toho, abyste zkontroloval tohle z toho, tak prostě out of memory. Dopadnete z out of memory, protože Grizzly tady nebude blokovat to, jako normální servlet output stream bude blokovat output. Že prostě když klient bude nějaký pomalý, tak to se zablokuje, Grizzly to nezablokuje, takže teoreticky to může spadnout na out of memory. Proto doporučujeme používat ty write handlery. Ještě nějaké dotazy? Okay, so let's move on to WebSockets. So WebSockets is how many of you just interested does anyone use WebSockets in development, in production, somewhere? Okay. So it's pretty new standard. It's it's pretty popular on the internet right now. So lots of talks about WebSockets because it's really supposed to replace some tricks, some how to say that, some approaches with like Comet, for example. Zbigniew before me, he told about Comet. They use Comet, for example. And WebSockets, it's exactly technology, or not technology, but standard, which is supposed to replace that the stuff like Comet. So in order to, so if you want really full duplex and bidirectional communication over standard, which is which you want like HTTP-like bidirectional and full duplex communication, you use probably you may use WebSocket instead of Comet because of actually I'll discuss that here. So what WebSocket is? You can think about WebSocket. It's pretty similar probably to HTTP in some respect. At least it looks like HTTP. It's not the same, but it looks like HTTP. So, and what are benefits of WebSockets? So first of all, they are unlike HTTP, they are bidirectional. So you can actually send information like client to server information, server can respond to client, client can send again the same another information to server. So this communication, WebSocket is really like, it's kind of socket, but in Java EE, for example, yeah, say Java EE socket, we can think about that. So it's really like, it looks like regular TCP socket, but it's really like web compatible. And for example, some HTTP proxies, HTTP and all kind of firewalls have to know about WebSockets and allow WebSockets communication. Because if you try to use some tricks like Comet with like on the internet, where you have lots of where you have proxies, you have firewalls. Firewall or proxy may deny or may reject your connection if it decides it looks strange. Because if you try, for example, in Comet, there is one approach in Comet when you send request and then trying to send lots of responses on the same connection, using the same connection. So it may work, for example, but not all the time, because some proxies, some firewalls will decide, okay, I see request, I see response came, but when again some data, you are trying to push some data which is not related to this request, so it's probably something is wrong, so it just closes this connection. So, but WebSockets allows you, like, supports this kind of approach, this kind of feature, but at the same time it has to be proxy and firewall friendly. So firewalls have to allow this kind of communication on WebSockets. So as I mentioned, it's bidirectional, it's full duplex, so you can read and write at the same time on a WebSocket. Again, unlike HTTP. It operates over single TCP socket. So one WebSocket is actually, it operates over one single TCP socket. It's HTML5 standard. So as I said, standard means firewall and proxy friendly, which is important. Again, there is some security supported, pretty similar to HTTP. It looks like HTTP, but really isn't. And WebSockets have some initial handshake phase, which we can see here. So it's WebSocket packet, a WebSocket request which comes from client to server. So you can see that it looks pretty similar to HTTP request. So it has GET method in it, it has host. It uses a standard HTTP upgrade header to say that we are going to upgrade this HTTP protocol to WebSocket. And just has some additional WebSocket headers which are used for some authentication, that to make sure for server to make sure that it talks to proper WebSocket client. So it's how server response looks like. Again, looks pretty much as HTTP response. So it sends status 101, means like we support switching protocols. We say, okay, we upgrade into WebSocket, and again send in some data to client, so client can understand that we want to communicate over some specific sub-protocol. Now sub-protocol, for example, chat protocol, and send in some hash information to confirm that client talks to proper server. So we have like mutual confirmation. So client sends some information to server, for server to make sure it talks to proper client, and the same server sends some information to client, so client will be sure that it talks to proper server. So and here, how in Grizzly some chat application may look like. So we can extend Grizzly WebSocket application and implement one method which is onMessage, which has information about WebSocket, which initiated this, which sent this message, and it has string which represents the actual message. So what we are doing this chat application, we are just iterating over all the registered WebSockets and sending this string to each WebSocket, which is to each registered WebSocket. So except this WebSocket which sent this information. So here we are iterating over all the WebSockets. We are checking that it's not the sender, and we send the message to a WebSocket. And here it's main method. Again, in Grizzly, how this WebSocket application might be registered. So again, we are using the same HTTP server API here. We are initializing HTTP server. We are registering WebSocket add-on on HTTP server, so that now HTTP server is able to process WebSocket connections. We are registering, we are creating like instance of our chat application, and we are registering this application on WebSocket engine and start the server. So as you can see, we can easily process WebSocket application, some regular standard HTTP handlers on the same HTTP server. So it's just pros and cons of WebSockets. So starting with pros, we have more of them. So it's WebSockets are effective, bidirectional, full duplex. It's bidirectional full duplex protocol. So again, unlike HTTP, so these are benefits over HTTP, standard HTTP protocol. So it uses a single TCP socket. It's standard, which is very, very important. So it's proxy and firewall friendly. The only cons is, as I asked you who uses WebSockets, and I didn't see any hand raised. So adoption takes some time. So really, people are currently they are starting to use WebSockets, but it's still like long time. We'll still need to wait until this is gonna be like real, how to say, real approach which people take when implement some kind of application. Do we have time? Sure, go ahead. That's a good question. I think it's like, it could be both. Actually, I think like you can find already, you can, like this standard, it's been approved, I think like a couple of months ago, maybe half a year ago max. So it's really new standard, but it is standard at the moment. So I can think like newer versions of some proxies and firewalls are going to support that, but maybe not all, right? And another point, it's adoption from developers, because you are developers, right? And nobody uses WebSocket at the moment. But well, I would say if you want to find something like proxy or firewall which is WebSocket friendly, you will find it, definitely. So it shouldn't be a problem. But yeah, but probably you have to go to your administrator, say, okay, I need to upgrade this, our like university proxy to support WebSockets because I want to implement some WebSocket application. And he says, okay, go to someone else, get approval, he sends you again to somebody else. So this might be a problem, like this process may take some time, but again, like I think you can solve it if you want. But yeah, but it's very nice standard, and I think it's going to be used like very widely, because it's really with HTTP you have all kind of limitations, because it's really a request response protocol, right? And WebSocket is not. Do we have time? Any questions so far? Okay, so just one more feature, Grizzly feature I wanted to cover here. Port unification, I just briefly mentioned it. So port unification, it's a Grizzly feature which allows you to deploy different services which are based on different protocols like HTTP, HTTPS, IIOP, your custom protocol on the same TCP port. So you have, say, port 80 open to internet, and you are able to use this single port 80 to expose all kind of services which are based on different protocols, like, as I mentioned, HTTP, HTTPS, IIOP, anything. So yeah, so pros for sure, it's easy administration. So when administrator has to just open one port to internet, and all the communication with internet will going to happen on this single port. So it just makes his life easier. Limitation, it's that communication has to be initiated by client. So on the server side you can, actually I can switch it here. So on the server side, in Grizzly, this is how a port unification looks like. So normally we have in Grizzly, I showed you a filter chain which represents HTTP server or HTTPS server. But if we have different services deployed on the same port, we have some kind of fork here. So we have filter chain here, which forks into different filter chains. So here we have HTTP filter chain, GIOP filter chain, for example. Here we you can have custom. Additionally, you can have HTTPS filter chain, which is secured HTTP. So, and Grizzly implements this fork as a filter. Again, it's called port unification filter. So you still have you still have filter chain, but now this filter chain is some kind of fork, you can see. Okay, yeah, and each protocol, like HTTP, GIOP, anything, in order to be deployed on this port unification filter, it has to be represented as finder, as protocol finder and filter chain. So protocol finder is responsible to understand if data which comes to server belongs to specific protocol. Say HTTP finder will take a look at the byte array which came and see that there is get method, some resource, that it's some specific HTTP request header. It will say, okay, it's my protocol, so I want this protocol, I want this connection, and data from this connection to be processed on this chain. So it redirects request process into this chain. If it sees some unknown header in a byte array, it just says, okay, it's not mine. Try another finder. So GIOP finder may decide that it's his connection, his data, so it redirects data processing to its filter chain. So the same with custom services, custom protocol implementations. And more examples and on port unification you can find in this link. Yeah, so we have also HTTP client, as I mentioned it, but I think we ran out of time, so any questions?